So that the next topic that we want to move into is what's called the curl of a vector field. And like I said before, earlier, the curl of a vector field is directly related to the idea of it's a new vector field which measures the local rotation of the vector field f at every point r. So this is defined as follows. And it should be no surprise that the divergence was introduced as a dot product. So now, the most natural thing to consider is the cross product of the vector field f with this del operator, or I should say the cross product of the del operator. Recall that the divergence of f is equal to this dot product, the del operator of the vector field f. So it's natural to consider what happens when we replace this del operator with a cross product. Exactly what we get is what's called the curl of the vector field f, sometimes also called the rot of the vector field f. And remember that this can be calculated by a standard rule, the standard determinant rule, or the determinant of the or determinant of the 3x3 matrix, where this is I hat, j hat, k hat, and this is the first vector, which is your del operator, and this is very important. This is the first operation here, and then p, q, and r. Oh, sorry, I started calculating and I didn't even write down what I wanted to write down. Let's move this down. So the curl, like I said, we define, instead of divergence, we were defined via the dot product. The curl we define as the cross product of this del operator with the vector field f. And this is going to give us something very, very nice. Because you remember that you go through and take the determinant of this expression. This will give you I hat times dr dy minus dq dz. You'll have minus j hat times dr dx minus dz dp dz. And then lastly you get plus k hat times dq dx minus dp dy. Or more simply, the curl of the vector field f is just equal to dr dx minus dq dz negative dr dx, or sorry, dr dy minus dq dz, dr dx minus dp dz, and lastly dq dx minus dp dy. So just like we said before, the curl of a vector field gives us a new vector field because each one of these is going to be we have 3 components, and each one of these is going to be a function of x, y, and z in general. Not only that, but this is giving us something very, very specific, right? This is giving us a measurement of something very specific for each one of these coordinates. So let's kind of, dissect this. Right? So the first component of the curl of f so we'll, instead of use curl round brackets here and then square brackets here. So the first component of the curl of f. What is this saying? This is saying that it's the rate of change of the z component of the vector field f, and this is with respect to y, and we're subtracting almost the same thing here, but it's the rate of change of q with respect to z, which is the y component of the vector field. And this is with respect to z. If you remember looking along our axes, this is saying that the first component of the curl is the rate of change of the z component of the vector field at a given point with respect to y in this direction, minus the rate of change of the y component of the vector field with respect to z. So what this is giving us, right, is the following. It's a measure, it's a direct measurement of rotation around the x-axis. So this is giving us a direct measurement of rotation of this vector field f around the x-axis. This is the first component of the curl. And I encourage you to go through and experiment with this and look at that the other components of curl are giving you the same, only with respect to their own individual axes. So for instance, the second component of curl is giving you a measurement of the amount of rotation of the vector field f about the y-axis. And the third component of the curl is giving you a measurement of the rotation of the vector field f around the z-axis. Not only that, right, but if we have a specified direction, right, suppose that we have a specific direction vector which gives us a line, so a specific direction vector we'll call it omega hat. It'll be a unit vector. So we have that at a given point r, this is the origin of our coordinate system. It's just a picture of the x-axis, the y-axis, and the z-axis at r. And I'll actually erase these. Just keep those in mind. At r, the vector field f might point in some direction like this, and then the curl of the vector field f will point in this direction right here. So some other direction, because and this is true at every single point has a separate curl vector. vector point because this is a vector field. Right? These are functions of x, y, and z. But suppose we want the rotation of this vector field f, or a measurement of the rotation of this vector field f about some line here, some arbitrary axis omega at this point right here. Well, we know how to measure that, right? We know that the dot product of any unit vector with any other vector is the projection of that vector in that direction. So the curl of the vector field f dot product with omega hat is exactly equal to, it's the same thing actually as, well, in terms of our nice curl formula, this is the curl, the cross product of the del operator with the vector field f, and it's the dot product omega hat. But this is giving us, right, if we look in terms of the magnitude of the curl vector, cosine theta, where theta is the angle between this curl vector and omega hat. This is the projection of the curl vector at that point in direction of omega hat, which is exactly the measurement of rotation around the axis defined by omega hat in that direction. And so this gives us a way of using the curl vector at any point to give us a measurement of the rotation of this vector field f around the axis omega hat. This is a really cool example. So I want to show to you why before, this is a big theorem. If a vector field f is conservative, then the curl of the vector field f should be equal to the zero vector. This is a huge theorem. Again, we need to impose smoothness assumptions here, right? The smoothness assumptions on specific quantities, right? F must be smooth enough. I'll be a little bit more specific with that as we go through and prove this theorem. So recall that if f is conservative, then there exists a scalar potential phi or a scalar field phi such that f is equal to the gradient of phi, or f is equal to d phi dx, d phi dy, d phi dz. Remember, we can also think of f as just saying that p is the derivative of the scalar function phi, the x partial derivative. Q is the y partial derivative of phi. And R is the z partial derivative of phi. And so the curl of the vector field F or the cross product of the del operator with F is equal to, from before, this vector right here and if we now use the fact that F is conservative, you know that R is the z partial derivative of phi, so this is saying the second derivative of R, and the first derivative here is with respect to z, or we are using the fact that R, not R, but phi. Okay, R is d phi dz. So plugging in right here, we get that this is going to be the second derivative of phi, first with respect to z, and then with respect to y. And then dq dz, well, q is the y partial derivative of phi. So this right here is the second derivative of phi, first with respect to y, then with respect to z. And this happens for each one of these components. So I'll make this a little bit bigger here. So when we plug in for R, right here, and this negative sign hits this negative sign, makes it positive. So when I plug in for P right here, I get the P is the x partial derivative of phi. And then we'll have the z partial derivative of that. And likewise, R is the z partial derivative of phi. And you have the x partial derivative of R. Then Q is the y partial derivative of phi. And this is the x partial derivative of Q. And lastly, P is the x partial derivative of phi. This is the y partial derivative of phi. So for this conservative vector field, the curl is actually this expression right here, with respect to the second part. It becomes the second partial derivative. And specifically, these are called the mixed second partial derivatives of phi with respect to the corresponding variables. And at first, this looks a little bit complicated, but hopefully from your multivariable calculus course, you'll recall what's called Clairault's theorem. Specifically, this is called Clairault's theorem. On the equality of mixed second partial derivatives and this is exactly saying the following. It says So if phi is defined on an open subset U of three-dimensional space, and the mixed second partial derivatives are all continuous functions, then they are equal to one another. So in this case, d squared dz dx is equal to the second partial derivative of phi in the reversed order. Or the x partial derivative of d phi dz is equal to the z partial derivative of the x partial derivative of phi. And so on and so forth for all the partial derivatives. So by Clairault's theorem on the equality of mixed second partial derivatives, as long as phi is a smooth enough function, each one of the components of this curl is going to be 0. And this explains, this is the proof of this theorem, and it's a direct explanation for why this is a sufficient test for us, right? For a given vector field, if all of the components of the curl of that vector field are, or one of these components is non-zero, then necessarily we're not going to have, the vector field F will not be solenoidal if any one of these components are not equal to 0. So this explains the tests that we went through and did, the test for whether or not a given vector field is conservative. Because this is saying that any conservative vector field has to have 0 curl. Right, specifically, it's saying that the converse of this statement is that if the curl is non-zero, then the vector field is not conservative. Now, this is where you need to be a little bit careful, though. Specifically, so like the converse holds. Right, the converse of the statement is that if the curl of a vector field is not equal to 0, then F is not conservative. Right, this is the converse of the statement that we just proved. So this holds, right, and this is a valid checking, right, is why we can use this as a tool for checking whether a given vector field is conservative or not. But note that this is not a by implication statement. This is only an if-then statement. So we can't go in the opposite direction. And that's a very important point. So be careful. There are vector fields, there are examples of vector fields where the curl is 0 everywhere, but F is still not conservative. So we'll see some examples of those as we kind of move further into this study of vector fields. So we defined a conservative vector field as a vector field for which there exists a scalar potential for that vector field. We can now also define what's called a purely rotational vector field. Is a vector field for which there exists a vector potential This vector potential is sometimes called A, such that the vector field F is equal to the curl of this potential vector A. And this is called purely rotational because F is essentially produced by a curl operation on the A potential. So a similar theorem to the above theorem for conservative vector fields applies for this purely rotational vector field as well, only it's reverse in some sense. It uses the divergence. So we can say that a purely rotational vector field or if a vector field is purely rotational, then necessarily F is divergence free. Which means that the divergence of the vector field F is equal to 0. Or solenoidal, as we defined it earlier. And the proof of this I'm going to leave to you. It's a good exercise. And it follows exactly the same lines as the previous proof for if a vector field is conservative, then the curl of F is equal to 0. By the way, this is sometimes why conservative vector fields are called irrotational. And this is also why this new theorem now, a vector field F is purely rotational, or it can be expressed as the curl of some other vector field F, or some other vector field A, then F is divergence free or solenoidal or incompressible. And quite possibly the most important theorem of vector calculus, of a beginning vector calculus course says that, remember, so this proof is going to rely on certain smoothness conditions on the vector field A, right? You're going to have to end up applying Clairault's theorem to the components of A. So it's going to guarantee that the divergence of any solenoidal field is 0. But what's called the fundamental theorem of vector calculus is the following. It says that, assuming these regularity conditions are satisfied, any vector field F, so this is not necessarily solenoidal, not necessarily incompressible, any vector field F can be written or expressed uniquely as the sum of an irrotational vector field and or conservative vector field and a solenoidal or incompressible vector field. And the proof of this is a little bit too long to include right now, but you can find this in the book and also in really any book on vector calculus. And what this means is that for any vector field F, we can express F uniquely as the sum of two vector fields, a conservative vector field and a solenoidal vector field, which means that any vector field can be written as the gradient of some scalar potential phi plus the curl of some vector potential A. And this is essentially why these two operations are so important, and why these ideas are so important. They in many cases simplify computations in physical computations involving any given vector field. So I mentioned earlier that there's a number of different really important simplification properties that we have for the divergence and curl. And these are related to derivative rules, the derivative laws, even for single variable functions. But a lot of these extend to divergence and curl as well. So here I'm just going to summarize some rules of operations. So some rules of operations for divergence and curl. And this is definitely not a summary of all of the simplification properties for divergence and curl. You can find a list of these in the book, in any book on vector calculus, but it's important to go over at least some of these and see how we would show and prove that these actually hold. So for this first property, we'll talk about, let H be a scalar field and V be a vector field, then the divergence of H times V is equal to H times the divergence of V plus the gradient of H vector dot product with V. And the proof of this I already kind of went over and talked about a little bit earlier. But it'd be a good idea to go over the proof of this and kind of verify this for yourself. So I showed how to do that, and it'd be a good exercise to do that. So a second important property you could consider with the exact same notation as before, the curl of H times V. And there's should be no surprise here that sure enough the curl of H times V is going to be H times the curl of V plus the gradient of H cross product with V. Now I'll quickly go over the proof of this. We know that the curl of H times V is going to be the cross product of the del operator with V, which we know will be from our formula for the curl. You can go through and directly show using our standard cross product calculation. This is going to be exactly equal to we need the curl of H times V here. From our standard curl calculation, right? This is in this example, the curl is of the vector field F equal to H times V, or HV1, HV2, HV3. So this curl is going to be equal to the y partial derivative of R, which is H times V3, minus the z partial derivative of Q, which is H times V2. It'll be the z partial derivative of P, which is H times V1, minus the z partial derivative, the x partial derivative of R, which is H times V2, or H times V3. And then lastly, it'll be the x partial derivative of Q, which is H times V2, minus the y partial derivative of P, which is H times V1. And sure enough, for each of these partial derivatives, we can apply the product rule, which gives us, when we apply the product rule to each one of these terms right here, we can kind of apply the product rule, and what we'll end up getting is the following. We'll get H times dv3 dy minus dv2 dz, and this will be plus the y partial derivative of h times v3 minus the z partial derivative of v2, or of h, times v2. And we'll have, I'm not going to go through and do the calculations here, but we'll have a similar simplification for the second component and the third component as well when you go through and do the product rule here. So lo and behold, all of this simplifies down once you've kind of plugged in and you've calculated out this second component and this third component. You can decompose the vector into h times the curl vector of v plus the cross product of the gradient of h with the vector v. And this is exactly equal to what we get when we simplify. So this is a very, very useful simplification many times when we have to take the curl of a scalar field times a vector field. Similar simplification, or a similar type of, a little bit more complicated, would be, say, let's say we want to take, we have two vector fields. V and W. What happens, say, if we want to take the divergence of V cross W? This is where things get maybe a little bit complicated. But it turns out that this is going to have a very nice expression. The divergence of V cross W will simplify down to the dot product of W with the curl of V plus, or minus V dot product with the curl of W. This is an example of a sort of rule that is a little bit more complicated than the other rule. All of the other rules that we've kind of seen have been very straightforward generalizations of the product rule, but here for this example that I just wrote down, it's not entirely straightforward, because you have the divergence of a cross product, and you have that this is simplified down to the subtraction of two separate dot products of curls of the given vector fields. So this is definitely a non-trivial relationship. But we can still go through and calculate this. So the proof of this, and direct proof of this, would be as follows. If you have two vector fields V and W, V cross W is going to be the vector field so you're going to have V2 W3 minus V3 W2, and then you'll have negative V1 W3 minus V3 W2, and then the third component of the cross product is V1 W2 minus V2 W1. This is what the cross product is in Cartesian coordinates. So we know that the divergence of V cross W then is going to be the x partial derivative of this first component plus the y partial derivative of this second component and then lastly plus the z partial derivative of the third component. And for each one of these we can apply the product rule, and when we do so we end up getting that it gets a little bit long here. For instance, this first term will be the dv2 dx times w3 plus v2 times dw3 dx minus dv3 dx times w2 minus v3 times dw2 dx, and then again I'm going to put this symbol here and this symbol here for the other long terms that we're going to have. I guess I'll go through and just calculate these so that you have an exact idea of how long this actually is. It becomes the y partial derivative of v1 times w3 minus v1 times the y partial derivative of w3. Then you'll have plus the y partial derivative of v3 times w2 plus w2 or v3 times the y partial derivative of w2 and then lastly the z partial derivative of this term right here, so you get the z partial derivative of v1 w2 plus v1 times the z partial derivative of w2, and lastly minus the z partial derivative of v2 times w1 minus v2 times the z partial derivative of w1. Okay, so this becomes very, very, very long. However, it's not hopeless. We can simplify this down greatly. the first thing that we want to notice, right, is that we can actually group the terms by the dot product here. We actually have two separate dot products here. Specifically, if we simplify and we collect all of the W terms, we'll start with W1. All right, W1 here is here. We have a W1 term here, and we also have a W1 term. Oops, I just realized we have a W1 term here. I have a typo right here. This should be W1, which means that this should be W1. And correspondingly then this will be W1. So I think that means that unfortunately there might have been a typo up here somewhere when we plug directly in. Oh no typo up there. Just a typo when I did the curl down here. The curl between these two vectors right here. So W1 then, we have W1 times dV3 dy and minus dV2 dz and then plus W2, and it will be minus W2 times dV3 dx from here, and then we have W2 times dV1 dz. Let me add a little bit more space here. Now for our third component, which is W3 times, and our W3 here is we have dV2 dx minus, and then W3 here is dV1 dy. So we've gone through and we've dealt with all of these terms. So this term, this term, this term, this term, this term, this term, and this is a rewriting right here. So this is all of these 6 terms that we've kind of dealt with, and we now have to add to that. And actually, I'm going to subtract from that the next collection of terms, which will be when we pull out the v. So we'll deal with v1 first. So this is going to be v1 times dw3 dy minus dw2 dz and minus v2, the v2 terms, and when we pull out the v2 terms, it'll end up being this first term right here, dw3 dx minus this v2 term right here, which is dw1 dz and then lastly we'll have plus There's a negative right here. So we'll plot the V3 terms, which will be V3 times dW2 dx minus V3 times dW1 dy. And I've written it in this order. We've kind of done this factoring in this way into two groups, because now what you hopefully can see is that right, the blue group deals with all of these terms right here. So I've just written the blue group here in this second summation right here, and the red group in this first summation. What you should hopefully see is that this first summation, these first 6 terms, it's just the dot product of the vector W with the curl of the vector V. In the second summation right here is the dot product of V with the curl of the vector field W, which exactly is a proof of that property. Right, so there are many other simplification properties, and I recommend you go through the book and actually prove a number of these. You can even find lists of these in the book, and also online as well. It'd be a very important thing to go through and verify some of these. Just to clarify and make sure that you understand exactly how you would go through and show some of these properties. And good exercise, great exercise would be to go through the list, any given list of vector identities or vector calculus derivative identities, and go through and prove and kind of figure out on your own what values what a given operation is equal to. So for instance, like what the curl, really good exercise problem would be to investigate what the curl of maybe a cross product of two vector fields is going to be. And I'm going to leave this to you as an exercise. It'd be a great thing to go through and do. It'll be long, right? Showing what it's going to be equal to is going to be a little bit long, similar to this right here. But the idea is that it's definitely possible to do, and it's a great exercise to become familiar with using the cross product, and specifically using the cross product and the curl and the divergence and all of these vector operations. But this is where we'll end the lecture for today. So thank you very much for tuning in, and have a great day.